everyone. First of all, thanks to the organizers for bringing this event together. And the second statement I would like to make is sorry. So I do know this is a tutorial. However, what I hear now is that it is supposed to be a tutorial uniting the topics of the day. That I don't think I will be able to manage. However, the aim of my talk is going to be, I'm going to explain one simple message. So you all heard about Majoranas, and the question that I encountered several times from various people and with various backgrounds and with various concerns was, are Majoranas good for quantum computation? So this is going to be the thing that I'm going to try to explain. So here's the plan. First of all, I'm going to indeed answer the question whether it's reasonable to expect that I don't want to make any interpretations about whether Majoranas were made or not. This question is perhaps too heated for now. It's also very exciting, but having Majoranas, how to make a quantum computer with them, is also a very interesting and legitimate question with no answer obvious a priori. So I'm going to show how to manipulate Majoranas in a fashion that seems relatively simple. I'm going to show how to braid them using this fashion and how to make possibly a quantum computer. This is the cheat sheet of Majorana fermions. Or Majorana fermion is actually not a correct name. The correct name is Majorana bound state. There's a Wikipedia article about the actual Majorana fermions that now contains a decent clarification. That was a joint effort between myself, Carla Beenacker, and an anonymous contributor that I believe is Xiaogang Wen. But so these are not fermions. They do have an almost fermionic commutation relation, but these are particles that are equal to their own antiparticles, and they square to identity. So this mathematical object allows to define a new kind of particle. It's non-Abelian. Two of these form a single fermion. And if there are only two, then there's only one way to couple them. Namely, there's only one non-trivial Hermitian term combining two Majoranas, and this is this product. The beauty of Majorana fermions is there's no possible way to make a term in a Hamiltonian that only contains one Majorana. So if you separate them and if you take care to not have any non-local couplings, then they form protected degrees of freedom. These are the fermion parities stored in the non-local superpositions of different Majoranas. So now, once again, there are very different approaches for creating the Majoranas. Many of them are in superconducting, semiconducting hybrid systems. There are more recent developments about how to create Majoranas in arrays of magnetic atoms, which are also a very active direction of research. But once again, let's imagine that we have Majoranas and think what we can do about them. So this is the most fun part about Majoranas, the braiding. The way you usually hear braiding introduced is in a way of coin and shell game, where you move Majoranas around, interchange them, and the final result depends on how you interchange these identical particles. There is, however, a much simpler interpretation that I like because, in particular, it allows to change the perspective and to understand the applications to quantum computation much easier. So let's imagine I have these 4 Majoranas. And let me say that they are, yeah?
When you say take 4 Majoranas, you mean take 4 operators, gamma 1, 2, 3, and 4? Is that what that actually means?
Right, yes, what else? Well, okay, right. So let me take these 4 Majoranas and let me consider them being in a definite state. So here specifically, let me introduce fermionic degrees of freedom corresponding to both of these pairs. And let me say these are corresponding to filled states of both fermions. Now I have described the full many-body wave function of the system. Importantly, it's not a straightforward step because in order to define these degrees of freedom, I need to define essentially a way to measure them. So I need to define a reference protocol of what I call a filled state, and it's not unique. So there is a fermion parity anomaly, so I could just as well define a different way of measure the same state, and it would look empty. But let's say I have defined a reference way to measure them, and it just says that they are filled. Now let me consider a basis change. So let me just ask, what if I define these to be fermionic degrees of freedom instead? What is the state of those? So if I perform this basis transformation, I will find out that the wave function is now in a superposition of both states being, of both of these fermions being empty and both of them being filled. So this is the essence of braiding. It shows that if you interchange Majoranas, so if I then physically would move gamma 4 on the place of gamma 2, the overall wave function would undergo a similar transformation. So this is the reason why, together with the protection of degrees of freedom, why Majoranas are believed to be good for quantum computing. The colors are somewhat of a problem. So there's a discrete version of braiding, which is much simpler. And do you see the colors here? Hardly. This is reddish, this is bluish. So this version is different from the original proposals that one would hear when discussing non-Abelian anyons, because it's discrete. So this is the minimal braiding circuit. It contains 4 Majoranas. It was made originally by these people, I believe. And it has 3 controllable couplings. So let's imagine I can tune all of these couplings in a time-dependent fashion, turning them on and off. Now, my aim is to interchange the red Majorana with the blue Majorana without actually moving them. So this means that I need to transform the degrees of freedom associated with both, or half a fermion associated with both of these Majoranas have to be in the end associated with the other Majoranas. Initially, let this coupling be turned on, which forces these 2 ancilla Majoranas to be in a reference state. So let them be empty. So once again, there's a single fermion corresponding to both of these. And if I strongly couple them and I let the system relax, I can hope that they will be in the ground state. What I will do now is I will perform a braiding protocol, which starts from turning on this coupling. That couples all these 3 degrees of freedom. Now, a simple counting shows that now I have In total, these three Majoranas form a single fermion, which will be still gapped because there are sufficiently many couplings turned on, plus a single Majorana fermion that cannot split. So there's a total of odd number of Majoranas coupled, which does mean that there is a single zero energy degree of freedom remaining now. It is going to be delocalized over all the three. Now, turning on the coupling at the top, I can move the red Majorana to the top, move the degree of freedom corresponding to the red Majorana to the top, moving the ancillus to the left. Now, a simple repetition of the same step does allow me to finish the braiding protocol. So further, I would delocalize the blue Majorana over the lower part, move it to the left, and then finally move the red Majorana to the bottom. So this is the braiding. And this protocol seems to be reasonably simple. So you can imagine some circuit where you control couplings and you move degrees of freedom. You still need to worry about being able to turn couplings on and off with exponentially large precision. So in order for this braiding to be protected, the couplings in the off state have to be really small. But there is a more important question even, namely the following. Are Majoranas useful?
Anton, could you?
Yeah?
What is really being moved? I suppose they're not really.
Right. So physical degrees of the bound states, as you saw, state. What is moved is the degrees of freedom in the Hilbert space associated with the original Majoranas. So there is the Hilbert space here has a degenerate ground state, doubly degenerate. You can associate you can define Majorana operators acting in this ground state, and these Majorana operators are the ones that interchange.
So the small that you're talking about, is there another energy? When you say couplings from offset, have to be small.
Right.
Some other energy scale?
There is the on coupling, and there are all the other energy scales. So if you, for example, have a coupling to some other Majorana over here, and you cannot turn this one off well enough, it will still pose a problem. So small is something to worry about, for sure. But at least in principle, this looks like a decent protocol. That's the only point I'm making right now. So there are two criticisms or concerns that appear when discussing the applicability of Majoranas for quantum computation. The easy one and the hard one. The easy one is what one hears from anyone who have learned about anyons and topological quantum computation. Namely, the braiding of Majoranas only allows to implement all the Clifford gates, which means that these gates form a finite set of operations and essentially discrete rotations of the Bloch vector. So that means that Majorana are not good, and all the quantum Hall Majorana literature resolves this issue by saying, well, we need to supplement Majoranas with an extra non-universal operation. But there's a trickier thing about Majoranas which is different and which also makes them non-universal. Namely, Majoranas are essentially linear combinations of fermions that appear in a mean field Hamiltonian, so in a quadratic Hamiltonian. So essentially, when thinking about Majorana fermions, one can consider them Majorana bound states, one can consider them non-interacting fermions, or one can consider a superconductor with Majoranas a non-interacting fermionic system, which makes them all wonderful and easy and joyful for many simple-minded people like me. But the problem about non-interacting fermions is that they are always easy to simulate on a classical computer. which means it does not matter how you couple pairs of Majoranas, bring them close together, bring them apart, braid them anyhow, it will still be classically easy. So the answer for this, if one does not have interactions, there will be no use for Majoranas. However, there is a protocol. Yeah?
Can I ask a question? I mean, these are two very different things, right? I mean, the first one is a fundamental thing about Majoranas, and the second one is actually a property of the Hamiltonian, right? And if you say something about, Majoranas emerging from non-hacking Hamiltonians, this is true to the means at that point. But on the one hand, the Discrete description is, of course, the energy description of the interacting Hamiltonian,
Yeah.
which is very hard to solve using a classical computer. And on the other hand, there have been many proposals on also realizing Majorana fermions in interacting systems.
Right, so the statement is like this. As long as you can describe the system in terms of a quadratic Hamiltonian, doesn't matter what the original degrees of freedom come from, and yes, the superconductivity is not a non-interacting phenomenon. But if you can describe them as a quadratic Hamiltonian, then whatever you can do afterwards will not be good enough. So you need to include something beyond just Majoranas moving and coupling pairwise. So the reason why Majoranas are good for quantum computation, on the other hand, is because they allow to implement, as far as I could judge, the only current scheme for quantum computation. So if you look into any domain of quantum computing, would it be quantum error correction, quantum repeaters used for long-distance quantum communication, anything essentially relies on a single protocol, which is quite mind-boggling for me, because these are problems that are not necessarily related. One appears in an attempt to protect many qubits, or to protect arrays of qubits from errors. Another one is for sending information. And Majoranas are appearing in a completely different domain, of course. So the statement is like this: Majorana is allowed to implement essentially the only protocol for reliable quantum operations, called magic state distillation. It was initially devised by Bravey and Kitaev. And the essence of the protocol is making a computation that has noiseless Clifford gates universal by supplementing them with one non-universal gate. The protocol works in the following way. First, you create several copies of the non-universal gate applied to a reference qubit. The most common choice of the non-universal gate is a pi/8 rotation. It's the half of the Majorana braiding, or square root of the Majorana braiding operation. Then, by using a bunch of extra protected gates, you can and consuming all these copies of an unprotected gate, you can create a new copy of an unprotected gate that has a higher fidelity. The reason why this protocol is very popular is because it has a very high error threshold by basically shifting all the error tolerance to one part of the protocol. And the reason why Majoranas are good for magic state distillation is because Majoranas, unlike surface codes, provide all of the protected operations for free. Meaning, Majoranas already have protection from noise when they are separated, but also Majoranas provide braiding and other operations that do allow to implement the protocol. So specifically, the constituent parts are the following: braiding, obviously, measuring a fusion result of two Majoranas, the non-universal gate, that's the phase gate, and that's the one that enters the protocol, or the unprotected. This one has a continuous parameter, and so this one will be susceptible to noise. And finally, in complete agreement with what I said just before, one needs to measure a joint fermion parity of 4 Majoranas. So one needs to measure this operator. As you can see, it's not bilinear. It's interacting, and that's why this is not only a decent quantum computation scheme, but also a working one. So it is a universal quantum computer. Right, so the advantage of the protocol, once again, is that the error of this gate can be up to 11%. And if there's only 1 degree of freedom which can change, or which can be noisy, the alpha, this translates into some very, very liberal constraint on what values alpha can take. I think it's a relative error of some 30 to 50% or something of this order.
Why is it necessary? Why is it important to measure the parity of combination of 4 gammas?
Okay, so first of all, as I said before, if I would claim I have a good error tolerant protocol for quantum computation without this step, you could say I only do anything with bilinear fermionic operators, which means it's a non-interacting fermion system, and that one must be possible to simulate cheaply on a classical computer. There's a paper from, I think, Di Vincenzo and Benacker proving this. Overall, I think the main idea is that you can, with non-interacting fermions, you can deal with determinants, basically. So you can reduce the Hilbert space and keep track of determinant of the Slater determinant.
Okay.
I don't know the technical details of that one.
Anton?
Yeah.
And when, so you have 4 points, and so the last 3 are kind of mathematically well defined, but the first one is just word. So do you assume that what you mean is you can replace interchange gammas in the product? Is that what you mean in this slide?
Right. So actually, if I can couple to Majoranas, that's, as we already agreed, it's almost like braiding. So so actually, this point is reduced to this one. Also, I could throw away this point because if I can measure 4, I can use 2 reference ones. But yeah, so in the end, I do mean that I need to have a protocol that would interchange degrees of freedom corresponding to Majoranas.
So it's not a permutation.
Yeah, right, exactly.
Okay.
Right, so as far as, yeah?
When you say measure Majoranas, what exactly do you mean? So you just locate this bound state or something?
So I need to execute a non-demolition projective measurement on either of these 2 operators. Not locate the bound state, measure the collective state of the degrees of freedom stored in those. Right? I mean, just finding a Majorana bound state doesn't tell you anything. That's the essence of their topological protection, of course. I mean, measure their joint state. Moreover, the tricky part, of course, about this one is that it cannot be reduced to measuring joint states of 2 Majoranas because it's not a projective measurement on the state of gamma 1, gamma 2. It's a more complicated operator.
So, Anton, in principle, how would you measure? So I guess if I have a single pair of Majoranas, in principle, if I bring them close, then I can just determine locally whether that state is filled or not. That's
Yeah, right.
How do I measure this thing for? I have to bring them all close and.
Right. That's so. First of all, once again, as we discussed previously, if you bring 4 close, you still have a bilinear Hamiltonian between all of them. It's still non-interacting. It's still not good enough.
Yeah.
Second, I have scrolled to this slide for the 3rd time now. That's the answer. So there are, as far as couplings of different electronic degrees of freedom go, I know of 2 ways. There may be more, but I think these two are rather general. So first of all, I can indeed bring two Majoranas close and make their wave functions overlap. And second, I can put Majoranas on a small capacitor that has a charging energy. And the interplay between Majorana degrees of freedom and charging energy was, well, it seems simple, but it still took quite a while to realize that it exists, and it was first reported by Liang Fu in his paper Teleportation through the Majorana Medium. But what he observed is essentially the following. If I have a finite superconductor with a finite charging energy, then the fermion parity of this superconducting island must be equal to the charge parity of the superconducting island, because literally every single charge comes from an extra electron. That means that the capacitive energy of the island must be also sensitive to the state of Majoranas, just through this constraint. Now, the beauty of the coupling of Majoranas through charging energy is that it can be used as the only ingredient, and it can be used as a way to implement all of the protocol. It can also be used to play around with various topological phases, make toric code with Majoranas, and as I heard from Eran, he's right now working on it and maybe going to say a few words about. Well, okay, I don't know about what you're going to talk about, but it is possible to implement quite interesting phases by coupling Majoranas with Coulomb energy. So now, if I say I have a finite charging island, finite superconducting island with a charging energy, this immediately brings me to a very active domain of superconducting circuits, mesoscopic superconducting circuits. Namely, let me introduce the key building block of everything I'm going to talk about later. This is a superconducting island. It hosts 4 Majoranas, this is just for the sake of illustration. And it has a DC squid that works as a, so how many of you are familiar, so please do interrupt if I am going too fast, because I do realize that people here are from different communities. So I have a split Josephson junction with flux threaded through it that allows to make this Josephson junction act as a tunable one. So there's an overall Josephson coupling between the island and the ground that has its strength proportional or dependent on the flux put through this middle loop. The reason why this strength is important is because the Josephson coupling allows the Cooper pairs, not unpaired fermions, but Cooper pairs, to float in and out of the island. And so it is a conjugate term to the, or it counteracts the charging energy of the island, which just counts the number of charges on it. So this means that very crudely, if I have the Josephson energy very small, I can measure charge. If I have the Josephson energy very large, the charge is completely masked from the environment. More specifically, the charge operator is a canonically conjugate degree of freedom to the phase, and the Majoranas enter the Hamiltonian through the constraint, through the parity constraint, namely the total number of charges, the parity of the total number of charges on the island has to be equal to the total parity stored in the Majoranas. So now, another important thing to realize when trying to make something non-trivial with by coupling Majoranas is that charging energy alone is not quite enough, because if I just have many islands hosting Majoranas with charging energies interacting with each other, there will be a lot of conserved quantities, namely every single parity of every island will be conserved, and therefore there will be no non-trivial evolution at all. So I need to also couple Majorana degrees of freedom from neighboring islands, and this can be, hopefully, having Majoranas. I'm willing to discuss how exactly to make this. This hopefully can be done by just bringing Majoranas from neighboring islands close to each other, and that splits the degrees of freedom between them by now famous 4-pi periodic Josephson effect. This term this term in the Hamiltonian does two things. First of all, this product flips the fermion parities of both qubits, of both islands, because it anti-commutes with the product of the Majoranas. This term, the cosine phi 1 over 2 minus cosine minus phi 2 over 2, brings a single charge E from one island to the other in either direction. So once again, obviously, since this is a physical term, it has to satisfy the constraint, namely that the parity of the fermion parity of the Majoranas has to equal the charge parity. So now I can have there is an important simplification of the Hamiltonian of a bunch of charged islands with Majoranas. Namely, one can just use the constraint and substitute it into the Hamiltonian by using this gauge transformation that results in several effects. First of all, it does make Majoranas appear explicitly in the Hamiltonian and not through a constraint. Second, it makes all the couplings 2-pi periodic. And the physical meaning of what I have done right now is I have arbitrarily assigned charge E to every single state of Majorana fermions on every island. This is not a unique procedure because I could equally well assign a charge plus E or a charge minus E. So some couplings look odd after this transformation, but it's still a correct Hamiltonian. So now I have written everything down, and I can solve the system. And in particular, I would like to make several simplifications. First of all, if the charging energy is large, then the phase degree of freedom is completely spread out over so the phase of each island becomes not very definite, so the Hamiltonian becomes just, it's not possible to control Majoranas in this limit. So to implement a kind of discrete protocol, I need to be in the regime when the Josephson energy always dominates, and that means that the phase of every superconducting island is well defined and is always close to its classical minimum of energy, namely phase equals to 0. In this limit, solving for the spectrum of each superconducting island is not a super simple but a straightforward task. So let me just remind you of the Hamiltonian of an island. It has an unharmonic potential, cosine-like, and a quadratic term which acts like a mass with gate voltage or with Majorana parity acting as a constant vector potential. So it's a particle in a ring with a cosine potential barrier applied to the ring and with a magnetic flux threaded through the ring.
Sorry to interrupt. So before you couple that qubit with 4 yellow dots to another one, I don't have any ways to actually see that they're Majorana fermions.
That's right, absolutely. Yeah, that's what I also said. If you don't couple them, they look very, very boring, just like a trapped quasi-particle. Well, it's not quite true, and as drawn, indeed, that's true. I could, however, couple the two Majoranas together, and that would be non-trivial. And that's actually something that I was working together with my collaborators on, but that's a sidetrack. Anyway, so in the limit when the Josephson energy is large, the potential barrier is deep, So it looks like a harmonic, like an almost harmonic potential with slight unharmonicity. There are discrete states. There are residual, there is residual sensitivity to the fermion parity of the Majoranas that originates from this phase particle tunneling around the unit circle by 2 pi, or around in the phase space. This is the phase slip process, and it does add an extra term to the Hamiltonian that is proportional to the fermion parity. This term, since it has tunneling as its origin, is exponentially suppressed in the ratio of Ej over Ec, depth of the potential barrier times the particle mass. And the important parts for manipulation of Majorana fermions are going to be the following. First of all, the ground state of the system is sensitive, or the lowest level of this harmonic oscillator has an extra contribution proportional to the fermion parity. So it has some energy E0 plus U0 times parity. But also the transition frequency, or the energy difference between the excited state and the ground state of the system, has a term proportional to the same parity just as well. Now, manipulating such a system is by now a standard technique in superconducting qubits. In fact, a superconducting island with a charging energy that is much smaller than the Josephson energy is called a transmon qubit, and it can be very efficiently coupled to a transmission line resonator that allows to drive coherent transitions between the ground and excited state, and measure the state of the qubit as well, or measure the transition frequency. Moreover, I remember I mentioned that increasing the Josephson energy allows to exponentially suppress the charging effects. Also, this phenomenon was measured in the transmon qubits. This is an experiment from Yale from 2009 or so, right? Probably. Where in essentially the same circuit, controlling the Josephson energy, they have observed the change in the splitting between the ground and excited state was going down from 74 megahertz to 0.8 megahertz. So good 2 orders of magnitude in a circuit that was not even supposed to have this exponential tunability. Meaning it was not designed to make this range as broad as possible. Meaning the advantage of the system is, of course, the fact that you can suppress the sensitivity, but right, okay. Finally, there's still one more ingredient that needs to be thrown in to make Majoranas computationally universal or suitable for implementing an interesting scheme. And this one is actually, I would not be able to prove why it is required. And I don't know of anybody who can. I have discussed it with several people. Namely, I believe that putting Majoranas with charging energies and Josephson energies on a line is not good enough. Somehow it doesn't seem possible to push the degrees of freedom through each other without messing something up in the middle. No matter how you arrange the chain, no matter how you make the non-local charging energies, it just doesn't seem to work. I will pose this as a conjecture right now, but a consequence of the linear layout to be insufficient is the need for a trijunction. In such a trijunction, the 3 Majorana degrees of freedom coming close together, they are always coupled. There's no good way to control this one. There's always one fermionic degree of freedom that splits. It's exactly similar to what I discussed when showing the braider. And there's one collective Majorana degree of freedom that is spread over all the 3 islands, and that depends on the couplings between the different islands. And it is a linear superposition of all these 3. So effectively, when you see such a circuit, it actually works like the braider that I discussed before. Namely, there is a controllable coupling, controllable by this flux, controllable coupling between this Majorana and the central one. Likewise, a controllable coupling between this central Majorana and this fermion, this other Majorana, and finally this one. So this junction is just a braider implemented using capacitive coupling. So now we have all the building blocks, and we can combine them together and try to see how to make something more useful. For example, this now becomes a relatively straightforward combinatorics exercise because all the building blocks are in place. So one obvious question: how can we demonstrate the braiding using such couplings? So what we will need is 6 Majoranas. This number is non-negotiable. Specifically, there are 2 Majoranas that have to be braided. There are 2 ancillas that need to be there to implement the braider. And 2 more Majoranas are required, really 1, but they come in pairs, as a reference in order to implement a reference measurement. Because if I just had 4, I would be able to implement the braiding, but I would need to measure a phase in. So in the basis of the 2 Majoranas that are braided, the braiding operation is just a phase for 2 different states. I cannot interfere it with anything. I cannot measure the braiding readout. So counting the number of degrees of freedom in the Hilbert space, I need 4 controllable couplings. 3 are required, once again, to implement the braider. I don't think there's any simplification possible there. And +1 is for the readout. Finally, as far as the geometry goes, I could implement either a circuit with 1 trijunction like this, or I could have 2 trijunctions. And this one is somewhat easier because it only requires Coulomb couplings. I don't think this circuit is possible to implement using the same building blocks. So this is the same braider setup drawn in a superconducting circuit. These are the 4 controllable couplings. There's a large superconducting island, which is also the only one coupled to a transmission line resonator. That's the one used for measuring the coupling, or measuring the final state of these 2 Majoranas. And these 3 couplings control the braider. So the protocol here is very straightforward. One needs to initialize the circuit to measure the state of these 2 Majoranas in the beginning, decouple, perform the braiding, and measure the final state. If everything goes good, the prediction of what should happen in the setup is that after 1 braiding, the final measurement outcome should be random. It should be uncorrelated with the initial state. After 2 braidings performed, the state of the Majoranas has to flip. After 3 braidings, it should once again be a random state, and 4 braiding, not a random state, but the measurement outcome should be random. And after 4 braidings, the system should return into the initial state. Now, finally, coming to the initial question that I asked in the beginning of my talk, the obvious next step is whether I'm able to imagine an actual quantum computer or some kind of way to make this into an architecture. For this, first of all, I need a qubit. And there's another simple combinatorial constraint, namely this circuit is definitely not a qubit because it only allows to implement one kind of braiding out of the 3 possible. There are different ways to make a qubit, but I think all of them require an extra trijunction, with this probably being the simplest. So this is the neutral junction that I added. This extra coupling does not need to be controllable. It can be always left in the off state, which is peculiar because I now have a qubit made out of 4 Majoranas where I can only access 3 of them. These are the 2 reference ones, and one can show that every single braid is possible by tuning the couplings here. And now the next step from having a qubit to a quantum circuit is actually an amusing exercise in computer graphics. But it's not, well, okay. Namely, the only thing I need to do is copy-paste a qubit many times. So what you see now is one large superconducting circuit, or 2 large superconductors, whose relative parity I can measure by coupling them to a transmission line. And there are many qubits that are all designed in the same fashion, such that from every single qubit I can bring any 2 Majoranas onto the measurement, onto the island coupled to the measurement bus. Moreover, this any2 means that I can also bring the ancilla Majoranas, that essentially turns the qubit off from the measurement. So what I can do with such a circuit is I can specify a single Pauli matrix per qubit, which can also include sigma 0, so a trivial one. And then measuring the relative fermion parity of the bus and the ground allows me to is the measurement of the product of all of these Pauli operators, which together with coupling of these 2 allows to also implement the complete quantum computer, or the complete protocol. So this brings me to my summary. The Coulomb coupling is definitely a necessary ingredient to manipulate Majoranas, because one cannot implement a quantum computer without coupling more than 2 fermions. The Coulomb coupling can be controlled with exponential precision by using superconducting circuits. And this is a rather peculiar thing that I would like to emphasize once again. So when one speaks about topological protection of Majorana fermions, one usually considers the splitting of the states as a function of distance between the Majoranas. Superconducting circuits allow to control terms in a Hamiltonian within an exponential range in a completely different way. And there are several purely superconducting circuits that also rely on that exponential tunability to implement protection in a Hamiltonian. So what is happening here is I don't need to actually physically move the Majoranas together to break the exponential protection, but instead I'm using this alternative source of the protection that comes from the macroscopic coherence in superconducting circuits. And finally, in a rather entertaining and perhaps not yet relevant exercise, one can combine all the ingredients together to implement quantum manipulation and a reasonably looking quantum computing circuit with Majorana fermions. This is it. Thank you very much.